Hello, everyone. My name is Xuying Qi. I'm going to present our paper named JointViT, Modeling Oxygen Saturation Level with Joint Supervision on Long-Tailed OCTA. The oxygen saturation level in the blood is crucial for health, particularly in relation to sleep-related breathing disorders. However, continuous monitoring of oxygen saturation is time-consuming and highly variable depending on patients' conditions. Recently, OCTA has shown promising development in rapidly and effectively screening eye-related lesions, offering the potential for diagnosing sleep-related disorders. To bridge this gap, our paper presents three key contributions. Firstly, we propose JointViT, a novel model based on the vision transformer architecture, incorporating a joint loss function for supervision. Secondly, we introduce a balancing argumentation technique during data processing to improve the model's performance, particularly on the long-tail distribution within the OCTA dataset. Lastly, through comprehensive experiments on the OCTA dataset, our proposed method significantly outperforms other state-of-art methods, achieving improvements of up to 12.28% in overall accuracy. We utilize a vision transformer as our backbone combined with a linear classification head. The VIT encoder is pre-trained on COVID VIT and further fine-tuned via transfer learning for our downstream task. To augment the learned representation of VIT, we additionally perform post-training on the Command V3 OCT dataset as an initialization for our oxygen saturation prediction task on PROC OCTA. During post-training, the augmented OCT images in the Command V3 dataset are divided into K patches of size 16 by 16 and processed through self-attention layers, incorporating patch and position embeddings. Unlike OCT images, OCTA images in PROC OCTA are three-dimensional values. Therefore, they are initially converted into two-dimensional slices. Then they are performed balancing argumentation and divided into patches, which is similar to the post-training process. To address the challenges posed by the long-tailed distribution and several class imbalance in PROC OCTA dataset and Command V3 dataset, we propose the integration of balancing argumentation into the data processing pipeline. Unlike conventional data balancing techniques such as upsampling and downsampling, which often introduce biases or compromises critical data information while achieving class balance. Balancing argumentation employs random cropping, flipping, and rotation at arbitrary edges. Unlike the vanilla vision transformers, which uses image categories as supervision, we employ both oxygen saturation categories and exact oxygen saturation values as joint supervision. For classification, we utilize binary cross-entropy loss, which outperforms ordinary cross-entropy loss when combined with vision transformer. For regression, we adopt mean squared error loss for supervision. The weight of each loss in the joint loss is controlled by coefficient lambda. Assuming the model is denoted as t and the input image as x, the joint loss L can be expressed as follows. For a fair comparison, we used the test set accuracy to evaluate the overall classification performances of the methods. meanwhile using sensitivity and specificity to assess how the model handles both minority and majority classes in the long-tailed PROC-OCTA dataset. Inspired by the principle of k-fold cross-validation, we divided the PROC-OCTA dataset randomly into 3 folds. Each time, we used 2 folds for training and 1 fold for testing, repeating the experiments 3 times for each model. This approach ensures a fair and robust evaluation, particularly when dealing with imbalanced and limited data. The experiments are conducted with an optional lambda set to 0.99, and the ablation of different values of lambda has conducted in the following section. This achievement represents the state-of-art performance in modeling oxygen saturation using long-tailed OCTA. We performed experiments by varying the joint loss coefficient, lambda, to examine its influence on both joint loss and the overall performance of the model. The outcomes are detailed in Table 2 and illustrated in Figure 1. Notably, the results indicate that the model achieves optimal performance when lambda is set to 0.99. We have additionally integrated ablation analysis concerning the joint loss within the proposed JointViT framework. This involves substituting our joint loss with a modified binary cross-entropy loss, balanced BCE loss, which tailors specifically for addressing the challenges inherent in long-tailed image recognition problems. The results indicate that our joint design loss function, which combines BCE and MCE losses, consistently achieve superior performance combined to alternative configurations. We further explored the efficacy of utilizing the other backbones through ablation analysis, especially compared with the second-based backbone in comparative studies. The findings, as depicted in Table 4, underscores that our approach, leveraging a VIT backbone, continues to exhibit superior performance combined to alternative backbone architecture. We have additionally assessed the effect of post-training on our training approach. The outcomes illustrated in Table 5 indicate that incorporating post-training with OCT images from the commanded database V3 yields notably superior performance compared to the absence of post-training. Eventually, we proceed to incorporate ablations of our data processing techniques, specifically focusing on balancing augmentation. The results, as shown in Table 6, underscore the efficacy of balancing augmentation. Notable, our model demonstrates remarkable performance improvement with the inclusion of balancing augmentation. Oxygen saturation level significantly impacts the health, particularly in decaying conditions like sleep-related disorders. We proposed a novel model called JointViT, which incorporates a joint loss utilizing both oxygen saturation levels and categories for supervision. Additionally, we employed a balancing augmentation technique during data processing to handle the long-tail nature of OCTA datasets. Our method significantly outperformed other established methods, image recognition methods, paving the way for future utilization for OCTA in diagnosing sleep-related disorders. Thank you.